Have you ever stopped to wonder how your phone knows, like, instantly if your password is valid? Or how a simple vending machine seems to follow your commands perfectly? Well, today, we're going to pull back the curtain and look at the secret rules that power our entire digital world. Let's dive right into the super fascinating field of automata theory.
Okay, so how do simple machines think? It can really feel like magic when they make the right decision, but it all boils down to a set of rules that's surprisingly simple. Let's start with a really common problem to see exactly how it all works.
So it all starts with this student, David. He noticed that the soda machine at his bus stop was acting, well, kind of weird. Sometimes it works just fine, but other times it would just flash an error, almost like its internal rulebook was totally scrambled.
And this got him thinking, what if the machine wasn't really confused at all? What if it was just a simple system that had a little glitch in its rules? That one question, right there, leads us straight to the heart of how these machines actually operate.
And this, my friends, is automata theory. It's the part of computer science that studies these abstract machines. It's basically the playbook for all of computation, helping us figure out the limits and the capabilities of any system, whether it's a simple soda machine or a massive supercomputer.
All right, let's circle back to David's puzzle and see how the simplest model from automata theory can explain exactly what's going on inside that finicky vending machine. So David figured out that the machine operates in this really strict, step-by-step way. The model for this is called a deterministic finite automaton, or just DFA for short. It has three key states. First, it's just sitting there, in the waiting for a coin state. As soon as you put one in, bam, it moves to the coin inserted state. Then you hit a button, and it transitions to dispensing drink. See? If you try to do anything out of that specific order, the machine just can't proceed. It gets stuck.
And this quote just nails it, right? It shows you what makes a DFA so good at its job. It doesn't think. It doesn't get confused. It's just like a traffic cop. It follows a very simple set of rules to direct the flow of what's happening. No questions asked.
Now let's see how that exact same logic applies to something you probably do dozens of times a day: decoding your password. So imagine a system with a really specific rule. Your password absolutely has to start with a letter, and it has to end with a number. How does the computer check that in a split second? Yep, it uses a DFA.
Think of the DFA as a bouncer at a club. It checks your password one character at a time. If it follows the rule, like Apple123, you're in. It gets accepted. But if it breaks the rule, even by a little bit, like 123 password, you're immediately rejected. No entry.
And here's the exact path it follows. It all begins in the start state. If that first character is a letter, great. It moves into the middle state. It'll happily stay there for any more letters or numbers. But, and this is the key, it can only get to that valid end state if the very last character is a number. Anything else, the password fails. Simple as that.
But, just like that vending machine, these simple, memoryless machines, they have their limits. So what happens when the rules need to get a little more complex? What happens when a machine actually needs a memory? Yeah, think about the code that all our software is built on. It's packed with these nested structures, right? Like an if statement tucked inside another if statement. A simple DFA just can't handle that. It has zero memory, so it can't keep track of whether an opening bracket has a matching closing one later on. It gets lost.
So to solve this problem, we need to level up our machine. We need a Push Down Automata, or PDA. And what it is, really, is a DFA with a superpower. It has a memory storage unit called a stack. Okay, the way this stack memory works is actually so clever. Just think of it like a stack of plates. When the PDA sees an opening brace, it pushes it onto the top of the stack. Then, when it sees a closing brace, it pops the top one off. If the stack is totally empty by the end, you know all the brackets are perfectly matched. Pretty cool, right? This whole progression, from simple rules to rules that need memory, it brings us to the most powerful theoretical model in all of classical computing, and, really, to the very edge of what's even possible.
So, at the very top of this hierarchy, we have the Turing machine. Now, this isn't a physical thing you can go touch. It's a profound idea that was thought up long before modern computers even existed. It's a theoretical model that can simulate any algorithm a computer could possibly run. It's the ultimate benchmark that defines what it even means to compute.
And because the Turing machine is such a powerful concept, it helps us draw a line in the sand. It proves that some problems are solvable, sure, but that others, like the famous halting problem, which is basically trying to predict if a program will ever stop running, are fundamentally impossible for any classical computer to ever solve.
Okay, so why did we just go through all that classical stuff? The rules, the memory, the limits. Why does it matter so much? Because it's the launch pad for the next massive revolution in computing.
You see, to really get what's coming with quantum automata, we first have to understand the classical version. Our computers today use bits, always a 0 or a 1. But quantum machines, they use qubits, which can be a 0, a 1, or get this, both at the same time. It's this mind-bending property called superposition, and it lets them explore every single possible path all at once.
And the advantage you get from this quantum awareness is staggering. A quantum automaton could search an entire database in one go, finding what it needs in a tiny fraction of the time. This just blows the doors open to solving problems we currently think are impossible, and it could revolutionize everything from medicine to online security.
So when you pull it all together, you realize these abstract machines, these automata, they aren't just some dusty old theory. They are the invisible grammar, that fundamental set of rules that give structure to our entire digital existence, from the simplest little traffic light to the most complex artificial intelligence.
So when you really step back and look at the big picture, you see it. The simple deterministic rules we've talked about today literally built the digital world we live in. And that leaves us with one final and, I think, really exciting question. What entirely new realities will the strange and powerful rules of quantum mechanics let us create next?